Hi, everybody. Thank you for the introduction. So, robot learning. Interesting topic. And the question is, what can I do in 90 minutes? And what I really would like to accomplish is I would like to raise a little bit of awareness of this world of robots. And the main thing with robot learning is that these are closed loop systems, that systems that generate their own data, and then they learn from it, and then they act based on what they have learned and create new data. And this can go incredibly wrong. And that makes it so interesting. And just for a tiny little sample on the side, so fine. Many of the machine learning people are super excited. Oh, 99% correct. This is so cool. My classifier is so. Now, if you fall over 1 out of 100 times when you get up out of the chair, you would be very unhappy. So that's the problem. So we have somehow different constraints dealing with physical movement. And I just want to give you a little bit of flavor about what we care about, what we think about, some machine learning techniques which help us to do that. There's many more things out there, but I think the awareness is kind of important, that you actually see what robot learning is, and that this learning in those kind of systems is quite a bit different from being presented with a bag of data which you can analyze until you die. So let's see. A little bit of motivation. See whether it works. Fine. What do the people in the world care about these days? Well, there's multiple grand challenges. What do you want to accomplish in this next 100 years? And the National Academy of Engineering actually, like 10 years ago, or whatever it was, put out a whole bunch of challenges what people should accomplish. Among other things, we should actually try to figure out how the brain works, which is kind of cool. And all of you are here essentially, by now you're called AI again. And understanding how the brain works, how humans work, is essentially one of the brain artificial intelligence. And from the viewpoint of kind of robotics, motor control, it would be totally cool if you could understand how to learn complex skills. And you can put this into all kinds of examples like prosthetics, rehabilitation, brain-machine interfaces. And there's people here at Max Planck and in other labs who specialize in that. Just to give you one example, this is, for instance, a prosthetic arm mounted to a person who is missing an arm, and it's activated actually from leftover neural interfaces, and this person can actually manipulate them up a little. So this is cool. So this brings actually robotics together with signal processing, machine learning techniques. What's important is when you see a video like this doesn't work at all. Okay, this works sometimes really nicely. The bit rate which people get out of the human nervous systems and can transmit into a prosthetic robotic device is like 10 bits per second, 15 bits per second. It's completely set. And so there's a lot of intelligent robotic autonomy in this arm to make this actually work with relatively sparse data. Okay, other topics. Well, kind of cool to create humanoid robots. Everybody would agree it would be nice to have one. Somebody brings you little bracelets and brings it's just your humble slave forever after and cleans up after. And one of the big challenges in this world, if you can somehow understand brains, can we actually use that to synthesize brains and actually create robots which are super intelligent? And the applications in this world are endless, essentially. Assistive robotics is one of the very big topics which is becoming more and more popular. We're having a problem. We are creating, well, all of you grow older and older and older. That's the problem. You all most likely get 100 years old. And we don't have so many young people to take care of so many old people. So at some point, we need assistive devices which help us to manage our daily lives, also with older people who wish to live at home, for instance, rather than in a nursing. So, but there's other things like basically having robots help us in things where people can't help, like epidemics, hazardous environments, space exploration, whatever you wish. Pretty much think about everything which people do not want to do, or where there's not enough people there to do it. Robots at some point would kill it. So here's one really nice movie clip which I like. It's very short, from iRobot. And I have to press one more time, or do I have to click? Okay, my movie.
History. By Saturday, there'll be one robot to every 5 humans. These robots are the realization of a dream.
Let me do this one more time. Super fast. Going the wrong direction. I should somehow learn. Okay, something wrong.
We are on the eve of the largest robotic distribution in history. By Saturday, there will be one robot to every 5 humans. These robots are the realization of a dream.
So this is iRobot, the movie, about 10, 12 years old, and that's pretty much all what's good about it. The rest is all garbage. So very appropriate for that picture. So robot immersed in a human world, helping in all kinds of things. Now, whether hugging your kid is the most important thing. Trash might be fun, okay? Nobody would say that's a totally bad thing. Walking your dog, so why not? Many other ways, but kind of the picture they depicted initially was really cool. And the idea that robots are everywhere, part of the world. And then, of course, things go wrong. The robots get nasty. And when they're nasty, they get a red light inside of their chest. That's totally cool. I don't know who put that in. And then they fight the humans, and you fight the robots, and they end their head forever. It's a nice vision. So that's Hollywood. Hollywood creates cool visions. And I forget this. This is a commercial how you can buy a robot at some point. People work towards these goals to create robots which are amongst us in an interesting way. So this is actually what is called Geminoids, robots which look creepily human-like. And I use the word creepily since I guess you will freak out partially. So the 3 humans. She's hanging in there, I would say. He looks super cool. Okay, I totally like him. So the 2 of them are amazing. So these are robots which look very human-like. Okay, they look the best in a video from a distance. If you get closer by, you get creeped out even more. They don't have tons of cool mechatronics inside, but it's an attempt to basically create human-like robots. And there are other attempts to do that. So here we go. Oh, robot entertainment, why not? And okay. This is the robot, not those guys, okay? Let's double check. Okay, interesting. It looks kind of cool the way it's choreographed altogether. This robot is blindly spooling down movement patterns. It does not perceive, it does not touch anything, feel anything. The hands are purely static prosthetics. They have no degree of freedom. So it was just an attempt to make something which looks appealing to people. And, well, you judge for yourself. It is kind of cute and it's kind of creepy, so depending what you want. And it was actually really hard to engineer this robot. In humanoid robotics, one problem is people put motors in the legs and then you get really big legs and they don't look very elegant for a dancer, so they had to do a lot of work to get the motors out of the legs. Okay, so let's talk about the fun part. Now, make this a little bit more sober. I want to tell you a little bit about robotics. I just want to tell you a little bit about history, very, very briefly. A little bit of foundations of control, since control is really what matters in robots. A robot is not a standalone system without control. It doesn't move, and control is tricky. And then go towards learning topics. In robotics, we distinguish between adaptive control and learning control, and I will tell you a little bit about what that means. And again, it will be fairly brief, but I think you will get a feeling about what this is all about. So just going back, so robotics. The name was actually coined roughly 100 years ago by now. A stage play by Karl Čapek. It was called Rossum's Universal Robots. This is a picture from that. Again, this is the robot, that's the human. Robot has handcuffs that you can assume that robot not happy, thus robot kills people. All of them, except for the creator. If you create robots, you will survive, okay? Everybody else is dead. So it's actually very similar to the iRobot movie in some sense, if you want to, in terms of the bigger topic that people create slaves, and then the slaves get a little bit unhappy. So fine, this is a long time ago, and then it takes about 50 years roughly before people start to create real robots. And then you give a picture like this. So this looks like a human, in case you notice. And you give this to a bunch of engineers, and what they come up with is, okay, fine. So that is a typical industrial robot, which has dominated industry for 10, 20 years at some point. It's a Puma Unimate. It's a nice, heavy 400-kilogram robot which can precise positioning and manipulate the world. And if you're in its way, it will look. So the world of robotics, and I gave you this. You will get the slide as a copy at some point. You can look through the world, what happens over time, and this is basically here where the stage play was, and then pretty much around here is in the 60s, 70s when industrial robots started to become popular. Again, I don't go through this. Artificial intelligence and robotics in the 70s, 80s became an important topic, but it's really just in the last, I would say, 10, 20 years that robotics has taken off and made really big progress in terms of mechatronics, better computing devices, much better sensing. So things like the Kinect sensor, 3D sensor, which now gives 3D vision to every robot in a very cheap way, made a huge difference, I think. And so the world is currently shooting ahead. It's not shooting ahead as fast as machine learning and computer vision. That actually is quite a bit slower. Since robotics, again, it has these physical systems, and they're nasty. And they're not simply software engineered away. People have tried that. There have been various attempts in the last 10 years where people say, okay, let's take 50 software engineers and try to solve robotics. It did not work, which is nice. So that's the reason why we are still here for research. And what do you want in life as a robot? Well, I want commander data. He's so positronic brain, can lift everything which is heavy, but we're very far away from that. So I try to put some videos in there in case we still have more fun. So this is some history. So people studied robot juggling for a while, actually, in the past. This is actually fun because this is Claude Shannon. You should all know him because he's in information theory. And he was interested in robotics and juggling robots. And so he had a little juggling robot at home, and then people created similar robots as he did. This is what is called bounce juggling, and made more and more complicated juggling robots until you have now at the ETH, for instance, juggling quadcopters. It's kind of cool what people have been doing over time and how the field developed. Juggling robots are easy to study. That's why people do it. There's a certain math that you can formulate. You can do return maps and analyze them and stability and control laws, which make them just pleasant to work with to get started. Doing it on a big humanoid robot becomes much, much harder. Okay, so this was just super short history. Some relatively more dry things is the foundations of control. What do we care about when we work with a robot? So how do we do that? And control circuits are what matters the most to us. So we have these block diagrams. Many of you may have seen them before. We have something which is the robot. We call it a control system in general. Some people in the old days called it a plant, because it came from industrial robotics. And it's also important that the robot is embedded in an environment. So the robot is not isolated. So you always have to consider there's the robot in its environment, and they form together. This is what you cannot, this is what you try to manipulate and control. And this is, you do this with action generation. You put out motor commands, and you get feedback, and you have to process it to basically make sense out of sensors in terms of higher level percepts, which then can be used by the action generating system. And there's noise everywhere, of course, which can potentially contaminate what you're getting. And there's hidden state and all kinds of nasty. People have to put this into some form of equation so we can mathematically manipulate that. They often talk about a system model that is essentially modeling the robot mostly, or robot plus environment, usually written as some nonlinear differential equations. They have a state, they have some actions. They may be time dependent and there might be noise in it. And there's an observation model which basically simply says there's a true state of the world X. There are some commands which you apply. There might be time and noise. And what you can see is actually only a small subset of that. Why? Whatever it is. Like, if you have a camera, you get pixels. If you have a position sensor, well, you only get position sensing in a robot arm, but you don't get anything about velocities and accelerations. So you very often have to state estimate or uncover those hidden states and other states. So this is essentially perception. I can put computer vision into that equation as well. Nobody claims there's equations which look pretty. These are big subroutines which realize that pipeline information process. So what we care about in robotics is essentially just a very simple thing. We would like to give a control policy. And Jan Peters already told about reinforcement learning and used this word, I think, quite a bit. So you should roughly know that. It's just a mapping from state to actions, potentially time dependent, potentially parameter dependent. That's really all what you care about. And then the question is, how do you actually represent these things so you can work with them? So how do you create this action-generating function? And that is essentially all the research. If I could get a function for every task of my life, like vegetable chopping, tennis playing, walking, scratching behind my ear, I'm done. But it's really hard to create these things in generality. So what do people do? They basically try to make control circuits which have easier to understand functions. Some people talk about open loop control. You just have a desired behavior, you have a controller, it spits out motor commands, the robot executes it, and it's done. No feedback. Kind of a stupid idea, if you think about it. But it turns out in many applications, it is still a useful thing to do, particularly if actually your feedback is fairly delayed. So if you want to have a Mars rover do something on Mars, you just have to send in a bunch of motor commands, let it go for a while by itself, and then get at some later point a summary feedback whether it was accomplished. But there's no way over the transmission delay to close the feedback loop. It turns out all of you humans are terrible delayed information processing systems. So your nervous system is slow, as simple as that. It takes you about 300 to 400 milliseconds to process from vision to basically muscle activation. Sounds like nothing. Sounds like that much. In control, this is terrible. It's incredibly delayed. And all of you, when you do make a fast movement like table tennis or something like that, you cannot do this with feedback. You have to make an open motion like that. Otherwise, your feedback would essentially not allow you to stop control. But the right thing is, of course, to do feedback control. This is when you get basically feedback back into the controller. And this is, in the end, how you can only assess whether you're doing the right. But both methods exist. And then just a little bit more about this. So this I just showed you before, general feedback control. But then people try to make it even simpler. So this nonlinear policy is a pain. Why don't we simplify it? If someone would give us a desired trajectory, a spaghetti through time of positions, velocities, potentially accelerations, then I could simply say, well, I want to realize that with my robot. And I simply compared every moment of time where I am and where I want to be, get an error, and I get a feedback, negative feedback term, actually, which I use to control the robot. This is the most common component in every robotic system, this negative feedback term, this negative feedback controller. I'll show you in a second how they look as equations. They're super simple, except you cannot arbitrarily create full motion with them. They basically can stabilize your system. OK, and then in the end, what you do in practical control, you have feedback, negative feedback controllers, and you have these open loop-like feedforward controllers, which basically work together to create motor commands. Often, these things are kind of given and manually twiddled. These feedforward controllers of a model-based controller, this requires either analytical models or learned models. So this is, for instance, one part where learning comes into robotics phase. OK, a little bit more. How do people think about control in general? Well, the one thing is still, you can have this control policy here as a function and not worry about substructuring that. In the world of reinforcement learning, which Jan Peters talked about, partially when they use function approximators to represent that, so it's also what AlphaGo and design testing to various of their reinforcement learning paradigms, they just put a really big neural network in there, no pre-structuring, which tries to learn the entire control policy from lots of data and also very intelligent tweaking of how the system works. People in robotics, in general, prefer this pre-structure. Since you can reuse things, you don't have to learn everything from scratch all the time. So this feedback controller, for instance, is always the same. Feedforward control, if it's a model of the robot in there, it's always the same. And then you have a planning device on the outside, which creates trajectories, which you try to realize. So this kind of creating substructures is very useful. And if you have many tasks, you obviously get lots of sub-policies which you need and which you need to chain together to finally accomplish a task. If I want to do something complicated, like I want to basically get a bottle, well, I have to get the glass off, I have to take this, I have to open it. Beautiful, the sequential decomposition, which you need to somehow represent. OK, so this is a little bit the control diagrams people deal with. And this is how people basically say what camp they belong to. Are you a planner? Are you a model-based controller? Do you don't want models at all? You're more a reinforcement learner. and you just want to learn policies directly, and there's different techniques how to do this. Okay, then how do these things look like in equations? Well, not very complicated. So a negative feedback controller usually consists out of a proportional derivative integral term. All what this means is the P term just looks at desired position errors, multiplies that with a gain, it's a positive number, and says this is a motor command which pushes me where I want to go. So if I want to be here and I'm here, then I have an error of this amount, multiply this with a number to get a force in this direction, and I will get closer. If I overshoot, actually the sign of my error term will change and I will be pushed in the opposite. Very simple. The same with derivative control. This is just about velocity errors now. And integral control is a way basically to overcome steady state errors. This is basically, if I want to be here and I'm here and I somehow don't know how to get there, I could basically take this error, basically multiply this error with some gain and increase my force to get there. Now, if I get a little bit closer, and I keep on doing this basically by ramping up in a sum of errors until I reach the goal. This is what is called integral. You use that all in your actually oculomotor systems quite intensively. Proportional and derivative control is realized mostly in the spinal cord in your muscles. We all use these kind of things. They're not as cleanly formulated in biology, but they're kind of part of pretty much every control circuit. They're very simple. The problem is these gains here, KD, KP, KI, you need to set them right. If you set them wrong, the system completely explodes. It goes unstable. So they are actually tricky little things to manipulate, and you can learn them to some extent, but it is not entirely trivial. Fine. Then model-based control. What is, so this was the negative feedback part. Now, the feed-forward part is often based on a model, and we like to use these kind of equations which look roughly like that. So this is what is called the rigid body dynamics equation of robotics. What the hell does that mean? First of all, it's a vector equation. Okay? These are multiple equations stacked on top of each other. And then it has certain meanings. There's this B term, which is actually, turns out to have all inertial terms, like masses and inertia matrices in there. And there's the C term, which has centripetal and Coriolis forces, and there's a G term, which is about gravity. And all of those together basically have to equal torque. This is physics. So here's something really important about robotics. We work with physics. Okay? Physics matters. You cannot overrule physics. Kind of silly, huh? But it's kind of cool. So you do learning on a robot, okay? So you can actually, these equations are learnable with a certain parameterizations where you have the inertial parameters, mass and center of mass as a separate linear vector in these equations. Now you take a whole bunch of data and you estimate that. And yes, you get all the unknown components in there, all inertia matrices, center of mass, mass component. But guess what? Your inertia matrix turns out to be negative definite. Huh. That's not physics, that's total garbage. And if you start to control with total garbage, guess what comes out? Garbage in, garbage out. As simple as that. So one of the big challenges people have in robot learning is actually inserting knowledge of physics into learning algorithms such that the learning algorithm does not learn something wrong. It's constrained by physics, which is an interesting and cool topic. Just to give you an example, this equation, all of you have seen mass spring systems. This equation also models a mass spring system, just a standard mass system, which is have as a control system. Okay. Now, a little bit more notation which people care about. Again, I want to give you this kind of feel for what we're dealing with in robotics. These equations here, we call them inverse dynamics because they map essentially an acceleration, velocity, and position of a robot into the torques which are needed to generate that. Okay? So this is actually what we often use in control. If I have a desired acceleration, desired velocity, and desired position, I can compute the torques to generate that, which is nuts. Forward dynamics is what we use in a simulation, in a physical simulation. So we just basically have to get this inertia matrix on the other side, solve for Q double dot, and it looks like that. Let's see. One more thing. People like to abstract these equations into what is called control affine equations, they look like this. If you compare this equation with this and then just make a translation that you can take a second order system, make it a higher order, first order system, then you can actually see that f of x would be, I think, the terms b minus 1 times c times g, and then there is b minus 1 times tau, this term. So this is a generic way, I will use this actually in a second. This is a generic way of writing these kind of the family of systems which we deal with, which are robotic systems. Yes. Yes. Isn't that annoying? I know. So that is the big miracle. So how do we do this? We find, yes, we learn how to walk with pretty much with one ear. And the researchers in locomotion struggling to have robots do anything a quarter as good as a little child. So yes. But this is not, but we don't know what the nervous system is doing, which constraints we have in build and which not. Maybe we have some good configurations and biases which just push us into the right physics, or we get so much good data that actually we constrain the parameters appropriately. But I don't have an answer to that except that I'm annoyed. All right. Okay, and then control laws, which you build out of all what we've seen so far, is usually you have a feedback controller, you have a feedforward controller. The feedforward controller, for instance, is computed from the inverse dynamics. As I mentioned, now I put desired in it. Otherwise, it's totally the same. Feedback is just in this a P law, so position error, velocity error, and that's essentially it. These are the standard ways how we control it. We use all this knowledge, we put it together, and do control. Okay, some properties. Now, industrial robots like this Puma Unimate, which I showed you before, they were originally all position controlled. Actually, they use only these PD controllers. They didn't use models at all. And they basically have made these P and D gains so huge that the robot is incredibly stiff. Stiff means like if you bump against it, it doesn't give in. It's like a rock, like your wall. Doesn't move. That's how it feels. Now, interesting is that all of you are actually amazingly squishy. So you can try now this with your neighbor, and the neighbor will give in or slap you, depending on how you do it. But all of you give in, so you have a completely different way of control. Now, this is what's called compliant control. The moment you go in the world of compliant control, you actually need model-based control. Since the idea of having stiff control is essentially that you put gains on the errors, position and velocity errors, make them super big, so that the system, the slightest error, it pushes back really hard. Now, if you want to be compliant, you cannot make these gains really high. And then in order to get accuracy in your control, you need actually models. And this is actually, this kind of robotics is what we are caring about these days. We want robots amongst us. They need to be able to bump into us. They need to be able to fall over, get up. They cannot just ruin the world or themselves. And that's where I really come. Let me see. Yeah, this. Yeah, let me just show you a video, a little much more fun. So this is an example of a robot, which initially is a little robot dog, which works with very high gain position and velocity gains initially. And it goes over terrain. It doesn't see those blocks. It thinks it's all flat. Okay? And that doesn't really work well. Yeah, it breaks, and it needs to be repaired. But if you put in a model-based controller, which actually starts to feedback forces and take dynamics into account, again, the robot doesn't see any of these obstacles. Suddenly, you can actually fumble yourself across those terrains, and you get a completely different ability how to control. Now, what this essentially tries to say is, control is super important. You can create absolutely stupid controller, and then you can put as much learning on this as you wish. It will never really work because you started out with the wrong thing. And you can have really good controllers which may not need no learning at all, and they're super proficient in them. So there is this slider. What do you want to do? If you want to do, for instance, robot learning, where do you start? Do you first try to create a robust controller which allows some learning, or do you just say, I have really crappy robot, a crappy controller, and try to fix that with learning. And that latter may not be the best idea. So I'm just moving forward. I don't have too much time. Boston Dynamics is a company which has been around for 15 years and has created really cool videos. One of their projects, like 10 years ago, actually until recent even, is this Big Dog project. And this is one of the early versions they have, which is really nice. This is a robot which is really good at locomoting and balancing by itself. The rest is remote controlled. It doesn't navigate by itself. But they created really an amazingly cool force-controlled, model-based controller which can go over rough terrain. It doesn't perceive the terrain at all. Okay? It just keeps on stepping. Yes, and that is robot abuse. These are old videos by now. I don't know, they're like 7, 8 years old. But they're still, I think, absolutely nice as an example what nice control can do. And you notice this is a compliant control. This robot is not stiff. It's not on an ice patch. And yes, they will admit they got super lucky with that. But it's cool that the robot can actually recover this way. So what's annoying about Boston Dynamics, they don't care about learning at all. They literally get it out. And they're super good at it. So let me move forward just a little bit. Okay, this is another. Okay, the video of Boston Dynamics got a lot of attention, and some people added their own version to that. Okay, I think they get the picture. Fine. Going towards a little bit of learning, adaptive control. So what is this about? And so people in robotics try to distinguish between learning and adaptive control. Essentially, adaptive control means a process where the system learns but doesn't fail. In very simple terms, if you're on an airplane, you would love to have an adaptive controller, since failure is not a good idea. If you just try to basically hit a soccer ball into a goal, you're totally fine with failure. So depending on which world you live, failure may be permitted or not. Adaptive control originally means learn without failing, which becomes relatively complicated, and so now I have to prove that you can do that. Learning control is usually trial and error learning. This is what reinforcement learning is all about. And what matters in the end is that the system is stable at all the time, together with the control law and the adaptation law you have. So let me see. I just, instead of doing this too much narrative, let me show you a little bit what people do in adaptive control in a very simple example. And I think you will get the feeling of what we would love to accomplish despite we can't all the time. So one form of adaptive control is called model reference control. It has a control diagram which looks like this. Here's the robot, here's a controller. This controller is adjustable, and there is some adjustment mechanism. And this adjustment mechanism gets information from the world. For instance, it gets a desired trajectory, and it compares that with what is currently actually happening, or this desired trajectory can even be changed by a model. So, for instance, people like to sometimes put simply first-order filters in a desired trajectory. Why? If someone gives you a step input, there's no robot in the world can follow a step input. So you want to smoothen it out. So you want to basically make things a little nicer. But anyway, there is, in the end, a mechanism which basically looks at an error or something like that and tries to adjust the controller on the fly. So how do you formulate learning in such a system? Fine. Now we go to this idea of a control affine system, since that captures most robots which we care about. So what is control affine? What does it really mean? So there is a part which only depends on states. There's a part which is linear in the command. That is really what matters. This is the control affine part. The controls are linear in some other term. And I want to make this much simpler so I can give you a very simple example where you understand how people create actually a provably stable controller, which is adaptive. So let's make this just a scalar system. X dot equals f of x plus u. I got rid of the g since the g is annoying anyway. And my control objective is to follow some desired position trace. And fine. I need to create a controller. So what does that mean? Well, I can put this a bit down. So my first, so how do you create a controller at all in this in a system like this here real fast? So x dot equals f of x plus u. Fine. If I want to control this that it follows a desired trajectory x desired, I can just create, say u. Well, what do I do for u? Well, let's cancel that f of x in case I know it. It's annoying. So I mean, this is the nonlinearity. Let's get rid of it. Okay, and then I add a component which is just a error-based negative feedback controller which says x desired minus x. Okay. Now, if I plug this in here, I would get x dot equals f of x plus c minus f of x plus kp plus x desired minus x. So these two terms cancel, and I'm just having a linear system which follows a desired trajectory. It's a simple linear system where if you choose this kp correctly, it's guaranteed stable, and it will do the right thing. So it's a useful little controller. Okay, and that was put in here. So here's the negative. And right now, given that we don't know f, we put an estimated f there, and this is what this little hat is all about. Okay, good. So now we have to make some assumption how we structure f. So typical learning people say, okay, it has to be parameterized somewhere. Somehow we make it super simple. We just make it a parameter theta multiplying x. So super simple linear parameterization. We could make this a basis function approach or whatever, but I want to keep it as simple as possible. And thus my estimated function is just theta hat, an estimate of theta multiplying. Good. So not too complicated. I plug this again back into my controller. Now that my f of x is just being replaced with theta hat of x. And that's essentially it. Oh yeah, I forgot there's also a feedforward term x dot desired, which is part of the controller. So what would I like to do? I would like to now use this controller, control the robot to follow the desired trajectory, simultaneously adjust theta hat such that it becomes as good as possible and never do something wrong. So that is the goal. Fine. We now take our equation, which we have, the simple scalar dynamical systems, which is the model of our robot, insert our controller, and get this. So the real theta, the real f of x, we assume is a true theta times x. And then we have that minus theta hat times x. So they don't cancel right now, because theta hat is not the optimal correct one. So there is essentially a remaining error. We basically characterize the error with theta squiggle, and we also have a tracking error. This is how far is my desired position away from the true position, and we call this E. This is all just kind of a prologue in order to set up that I can deal with the problem. And fine. After you insert now this new notation into this equation, which we have up here, then you get essentially terms combined, and you can write it in terms of errors. And you have an error E here and the parameter error there. And then you can, in the end, write what is called the error dynamics. E dot equals k times E times theta squiggle times. What you want is essentially that this error dynamics converges to E equals 0. And you want on top of that that theta hat is the right theta hat. The theta squiggle thing becomes 0 as well. So that's the error in parameter. Good. So this was just how to start formulating the problem. So now how do you actually do something which is actually functional system? You need to run this through a provable form that it's going to be stable. how many of you have been exposed to Lyapunov functions? Because a few, but not everybody. Good. Very simple introduction to Lyapunov functions. Oops, well, big. So Lyapunov functions are used to do proofs in nonlinear control quite a bit. And the idea is, people forgive me, I make this as simple as I can. So let's assume you have a system which has two states. They're called x1 and x2. And here we have something in the vertical axis which we call v, which is something like a potential function. Now, my control objective is to go to a particular point in this x1, x2 space and say, this is where I want to be, okay? This is my desired x1 desired, x2 desired. All right. Now what I'm going to do is I create some kind of a potential function, which usually looks like a parabolic bowl, which has its minimum right at where I want to be. And this thing has some parametric form, which I call v. And now the whole idea of a Lyapunov proof in this context is to say, wherever I am, wherever I'm starting, so when I'm in somewhere in the state space, that means I'm somewhere here x1, x2, but I'm also somewhere in this bowl. So I'm in a three-dimensional space like here. If I can create a control law which guarantees that at every moment of time, I go a little bit down the hill in this bowl, which essentially means dv dt less than 0. And there's only one way, or there's only one place where I can end up, that is at the goal. So if I can create a v and a control law such dv dt is less than 0 all the time, then I can prove that I will end up at my desired. So, fine. Lyapunov functions are such a very cool tool, except you have to make them up. And sometimes it's very easy to make them up, as in the example which I'm using. For generic systems, nonlinear systems, it's really complicated. It may not exist. But the interesting part is, just because you cannot find the right Lyapunov function doesn't mean at all that you cannot prove the system is stable. It just means you're stupid, sorry, or not creative enough, let's call it this way. So this is the problem of Lyapunov functions. You have to invent them. And some people are super creative, and some people made a big name out of their lives because they found a Lyapunov function to prove something. If you go back in machine learning, if you go to, what was it? Opfield networks, associative memories. One of the important things in the early 80s was essentially that John Hopfield basically found a Lyapunov function which could show that the parameters would converge into a stable configuration. Super simple by now. It's based on spin glass theory. Those of you who physics know this much better than I do. Anyways, so let's create a Lyapunov function for our little system. So just reminding you, my system, I just put this in here, is x dot equals theta times x plus u. Super simple system. We said we have a position error, xd minus x, and we have a parameter error, which looks like theta minus theta hat. What do we want? What's our objective? Our objective is to have 0 error and to have in position and in parameters. So I create a Lyapunov function where I now actually use this position error and this parameter error as my state. And I span a Lyapunov function over it, and I want the bowl actually have to be here at 0, since I want to have 0 in both of the states. Now this function creates a nice parabolic bowl. And it's actually written for a vectorial problem, so this could actually be just written as theta hat squared times some parameter sigma minus 1, whatever. The sigma minus 1 is just in there as a parameter. You will see why it's useful in here. Good. So that's the Lyapunov function. Fine. And then now I have to show that dv dt is less than 0. And we can go through this relatively quickly. You take the time derivative of that. You get those kinds of equations. Here we replace suddenly the squiggle with hat. The whole idea is if you take the derivative of the error, time derivative. Theta is the true parameter, it doesn't change. So if I write this properly, theta dot hat equals minus theta hat dot. That's just why somehow a change of sign comes in there. And you keep on putting things together, and you end up with v dot equals this thing. Cool. Now, our question is, can we show that this is less than 0 all the time? Well, minus k times e squared is a nice term I personally like. E squared is guaranteed positive, k is a positive number, so negative on front of it is guaranteed. This is negative. But the other two guys, they are not friendly. So fine, let's get rid of them. So we simply assume that this term minus this term has to be 0. Okay? And this is nice. Now I can solve that for theta hat dot, and I get the following equation. It's a simple differential equation which says theta hat dot has to follow this positive multiplier gamma times e times x. And that suddenly is a parameter adaptation law. It tells me how to change my estimate of my parameter over time. And if I do it in this way, I'm guaranteed that I'm having a stable system which will push that error to 0 and which will push the tracking error to 0 as well. So this is nice. This is in a very tiny little nutshell how to do a proof for an adaptive controller and show a system which controls and learns at the same time and is guaranteed going to the right goal. Neat. So this emphasizes the closed loop system. I just want to say this. The problem is, of course, this was super simple. Now, if I put this back into the full nonlinear control affine system, I have to do way more work. But it is to some extent doable. And now for basically representing the function, you use some basis function approach, usually some Gaussian mixture model or similar things. And then you can create nonlinear learning controllers which still are provable. Very important, when people in control theory talk about proofs in nonlinear systems, usually this only works by making assumptions. So they say, oh, certain things are bounded, certain things cannot exceed certain things. There's lots of assumptions which go in there before you can actually prove something at all. That gets more complicated, but it is to some extent doable. So here's actually a fun system. This is the same idea as the system I showed you, just basically it uses a full nonlinear function for f of x. And it represents them with a little basis function approach, which learns with local linear models how to model the nonlinearities of some kind of a Gaussian pump. Let me go back one more time. This learns literally in fractions of a second. This is incredibly fast. This is a system which automatically allocates kernels as it needs, then basically makes sure that this within stability proofs are correct, and approximates the function as good as possible. This is in some sense what we would love to have. And there's one thing really which I like. Learning in fractions of a second. There's a big difference. If you have a deep learning network, generally you have to learn over multiple hours with lots of data to make this work. It's a totally different philosophy rather than learning maybe just in a very local area, but learning on the fly in fractions of a second that you actually never have to represent the entire world. That's something which is specific to robotics. Actually, super cool. 20 years ago, Jean-Jacques Slotin at MIT actually had learning controllers on topics like that as well. It's just people reinvent things again with catching and whatsoever. He did this with a actually really nice Barrett arm, which is actually similar to an arm which is here at the labs. And this robot learned simultaneously its own dynamics model plus the model of the flying object so that it catches appropriately. And it did really well. And that's a solid nonlinear control. Okay, moving along. So I want to go over to learning control. And I want to talk a little bit about model-based learning control, coming back a tiny little bit to reinforcement learning, kind of complementing what Jan Peters has been talking about. Now, what's important, I need to keep you awake, so I'll show you a video. 2 years ago, there was actually a very cool thing in robotics. It was what is called the DARPA Robotics Challenge. The idea was to take human-like robots and putting into disaster scenarios a parkour of different things they had to do. And the hope was that these robots can solve these tasks proficiently and look really cool. That's essentially, many people thought, oh, DARPA is spending now $50 or $100 million on that, and maybe that is going to solve the robotics problem, and then the Terminators get better. And many of you may have seen kind of what came out of that. That's part. Now, does that play by itself, or does that press the button? Okay. So there was some finals in the end, and lots of very expensive robots started, and lots of very expensive robots actually crashed really to the roof. And they basically move in thousands of different ways. Like, I think this one lost battery power. Robots which basically think they grasp something and they actually didn't grasp it. Well, walking is not simple. That is when your gains go unstable, okay? Those PD gains, no good. Well, this guy completely failed. So let's put it this way. The robot Terminator is a little bit down the road. So, I will show you later a little bit about it. It was also very successful trials that people accomplished the task. It took them a long time. What a human could do in like 2 or 3 minutes, the robot took like an hour. But it's just, this was a couple of years of research with huge investment by the team. And it is just so hard to take a robot into a unstructured world. And fine. There's no learning on this. Actually, I should actually emphasize, all these robots were teleoperated. They could balance by themselves. They could do certain things by themselves. But in the end, they had an operator in a room far away, which could see what the robot sees and then could tell the robot what to do. This was not autonomous robotics at all. And still, it didn't really work so bad. So let me go over to learning control. And so here's a little bit of a generic diagram about all the things which happen in a control system. So you have visual input to the robot, you get spatial information, you get object recognition. Usually people think about 2 different paths these days. You may have a 3D camera, but the other thing is maybe some heavy-duty learning networks. In the end, you see what's in the world, action, posture of what's going on. You figure out where objects are in 3D. You give it to some kind of modular system which basically creates motion. There might be learning systems. Commands are generated by these whatever modular motion systems and then finally sent out to the robot and their feet. So these are all the different components, roughly, which belong to a robotic systems. If you think about what you could learn here, there's tons of things. There's coordinate transformation from visual to robot coordinates. There is unsupervised learning and classification problems, obviously, for object detection, segmentation, classification, whatever you want. There's control policies, how to plan with modular systems. There is reinforcement learning. Peter's told you about value functions. It's another form of what you have to learn in order to basically be able to control appropriately. There is models of the world, which we talked a little bit about, how the robot and the environment actually work. And I think kind of one little summary is that there's a huge number of function approximation problems in robotics which you have. And so people often in robotics care about function approximation quite a bit and look at what you can be doing. So let me see. Before you start learning, it is actually useful to think for a few minutes or days or weeks about what you try to learn. I want to just go back to these 2 kind of things. We talked about for a moment about inverse models and forward models. Now, forward models, these are the proper differential equations how a robot works. The robot is in a state which in a second order robotic system is modeled by position velocity. You give it a command, tau, and out comes an acceleration. That means the change of state of the robot. So this is a proper causal model. Basically, you are somewhere, you do something, something happens. The inverse model, for instance, which we have, where we basically getting this torque, this is actually inverting that causal model and saying, okay, if I'm in position and velocity, and I would like to have a desired acceleration, which torque should I use? Now, the problem is that inverse models are not always proper functions. They can be relations. And here's actually a nice picture, and this is actually from Mike Jordan 20 years ago in a publication he had, and he was actually still publishing on motor control topics. This is about basically if you have two spaces which are related by equations, and you think about a forward mapping and an inverse map. So let's take that gray area, and let's assume this point in this gray area, and or the entire gray area gets mapped into this other space to a point, which can happen. Okay? And if you now try to map back from this point into this other space, you will actually start some weird generalization which makes potentially no sense. So the idea is essentially, let's assume you are learning how to basically, you get a point here, it maps to this point. You get a point here, which maps to the same point. And now you try to turn this around and basically say, okay, what if I get this as input? What should be my output? What learning algorithms do, they take these 2 points and average them together. So it's the same input, 2 points that's meant to be noise. That means they would actually basically average roughly in the middle. Now, if this entire set which maps to this point is not convex, then you would actually start with inverse mapping and create something totally nonsense. Let's make this more plastic, much easier to understand. Here's a robot arm. Here's a two-joint arm. Has an upper arm, an upper arm and a forearm. So upper arm, forearm. It can reach to a target like this. It can reach to a target like this. We all agree on that. This is the same example, just now much more easy to understand. Take these two postures and average them together. What you're getting is the robot posture looks like this, and it reaches up here and will not reach that target. So in robotics, you need to really think about when you try to learn something, whether it's learnable. You cannot just assume just because someone gives you data, you can learn that. That is absolutely not true. It may never be learnable, ever. No matter what you use, deep learning, whatever, support vector machines, Gaussian processes, or the latest mumbo jumbo you come up with. So these things need to be a little bit pre-analyzed before, such that you use the right learning algorithm which can deal with that, or you reformulate the data problem in a good way. What you can, for instance, do, you can learn in joint space. So Zubin Garamarni at some point in his PhD thesis actually looked at problems like that and said, okay, don't try to learn a mapping, try to learn basically a joint density representation, and then basically marginalize. So I just wanted to emphasize for 1 second. Cannot assume just because you get data that you can learn something. Good. Besides that, so what are problems in robot learning in general, or in function approximation in robotics? So fine, we get large amounts of data from a robot. A robot basically generates a data point every 1 millisecond, 5 milliseconds, 10 milliseconds. So you get lots of them. They come in a stream, so it's continual data which comes there, and you would actually like to generally learn from that. And you live in a potentially really high-dimensional space. Like a humanoid robot with 50 degrees of freedom creates actually a 100-dimensional state space. Now, you will never in your life represent that state space. Okay? It's a very big space. You cannot fill that, and you can basically create data for 100 years, and it's not full. It is just race spots. So you need to simply assume that you get data as it comes. You cannot know in advance what's the kind of function complexity you deal with. You have to grow basically with the complexity as you go along. We would like to do fast learning. What does fast learning mean? Fast learning means, in some sense, data efficient. It means how much can I squeeze out of every data? Like support vector machine Gaussian processes do this really well. A deep learning system does not do this as well. It does not squeeze that much out of one data point. It needs tons of them. You want to be computationally efficient, since you want to be able to compute in real time. So our control loops, if they are run at 100 hertz or at 1,000 hertz, then you get just 1 to 10 milliseconds time to compute. So that's it. You've got to be done by this. And you basically, computational efficient means also that you don't use computation in order to learn from the data. Other things which are cool. Well, You don't want to unlearn something when you learn something new. This is a topic which is currently reborn. It was an old topic in neural networks in the 80s, 90s, and now with deep learning, people worry about this again. And you just add a new data set. How do you make sure you don't unlearn what previously represented in the system? So minimizing interference matters. Learning in very high-dimensional spaces, hundreds of inputs, or maybe thousands. The back of your head is a little thing. It's called the cerebellum. It's pretty much in charge with a lot of your motor learning. Now, every cell in the cerebellum, it's called a Purkinje cell, it's on the order of 100,000. So that's kind of the standard, okay? And all of you make sense out of that. I have no idea how, but we just have problems with a few hundred of it. So learning from lots of sensory data would be really nice. There's other things which are really annoying, actually, in robotics. That is, if you learn something like a model of the world and someone pushes you from the side and you have no way to perceive that this happened, all what you get is data which are not consistent with what you try to learn. It essentially becomes outlier, and you have to deal with this as well. So how can you get into this kind of learning? And I go actually a little bit back into some very simple, old, kind of nearest neighbor or non-parametric methods, but which can learn really efficiently in robotics. Just go back. So fine. Let's start with something super simple, linear regression. All of you presumably know linear regression. Very simple question. Basically, you assume that you have data, you can fit a line through that. The model you have is essentially that every data point has a little spring attached, and this line rigid stick, and the stick finds kind of an equilibrium position among all those springs. Which also tells you, many of you know that, if you have an outlier, that means a red dot which is out here. Good. Oh, yeah. As many people know, noise in linear regression is only in the output. Something which to sometimes think about. Often you have also noise in input data. That means you have also noise in X direction, which doesn't mean you need to do something different than linear regression. Anyways, but we go forward. The way linear regression works, I hope I don't have to spend any time on that. So you assume simply some output Y is some linear parameter vector W times state X plus some noise. We put this all into vector matrix notation, and I'm not going through that. You solve it for W, and this is the standard linear regression equations you get. Basically, all your data, all the input parts of your data in state X, and T is essentially the targets which you try to. So standard linear regression. Nothing profound, but a beautiful Newton algorithm which converges really fast and learns very efficient. As many of you most likely know, there is an online version of that, which is called recursive regression. And it's based on the matrix inversion theorem. And without going into all the details, essentially it allows you to estimate this kind of inverted xt times x matrix. This becomes P. You can learn this online, and you can learn the parameters online. The nice thing about recursively squares, it accomplishes exactly the same result as linear regression. It's an order square and square method, so it's much faster to do online than full batch regression. Fine. Linear regression. Most people know this. Boring. You can use it, however, in various ways. So you can now make it, actually, if you want to go into the nonlinear world, make it locally linear regression. So basically, here's a nonlinear function, and just basically try to find little local tangent pieces and try to do nonlinear function approximation with that. So why not? So you need somehow a local area. Usually if you do some kernel function, Gaussian function, whatever you want, you present that linear function with some kind of a weighted regression technique. And you can basically, if you can do this, you can piece nonlinear functions together in arbitrary ways. You can actually have many overlapping local models. Get something like this, so you get just very few which just cover the function sufficiently, and it works. So we worked with this actually many years ago, and just basically created algorithms which create little local linear tangent planes, use weighting kernels which are Gaussians, and basically combine the output a little bit like a Gaussian mixture model. There is recursively squares and gradient descent methods which can learn all parameters, so beta parameters, the distance metric which is used, the weighting kernels, and then combine all of these things. just for fun what these things can do. So here's a synthetic example of data drawn from some kind of a nonlinear function, 3D, just for visualization. And if you start learning with these systems, it allocates automatically local models by itself. They start out to be too wide. You get some over-smoothing. You train for a second longer. And these models basically start adjusting to the local curvature of the function you try to learn and get a fairly reasonable learning result. This system was actually used in this adaptive controller, which I showed you before. That is exactly this kind of locally weighted regression at work, creating kernels and learning and really, really fast how to get better. Let's see. It's an older video showing actually where a robot arm learned the model of a inverted pendulum and improves over time. The moment the model is learned well enough, it can actually create a controller which can balance properly. And it does this in trials. Again, the model, all of this is online learning. It's not very hard to learn, but it works really well. You can make it a little bit more complicated, but this thing balances forever. You can put this into more complicated systems. So this is actually a robot which learned how to do devil sticking, and that was then later on a humanoid robot. This humanoid robot actually learned its own dynamics model with locally weighted regression techniques, including then a task model of how this devil stick flies around, which allows it to create an appropriate control. The nice thing is it's all online learning. This is literally working in real time without any. When you use these locally weighted learning techniques, there's a little bit of an issue when you go into high-dimensional spaces that you worry, well, in high-dimensional spaces, you have to make the kernels big and you cannot represent things properly anymore. And I just want to quickly address that. The high-dimensional space issue is actually a funny thing. So if you take an example here, this is data which lives in a two-dimensional space. But if I put a magnifying glass on it locally, then actually the data just lives on a line. And this is actually what happens seemingly a lot in robotic data, actually in many other data, I think, which is generated by physical systems, that the data which is generated actually lives on really thin distributions. And I don't use the word manifold, since manifold is actually mathematical. I think the data is just generated in very thin areas. And we looked at this actually at some point. It was actually a postdoc of mine, Michael Zeller, and he put a very nice exoskeleton on and basically collected a couple of gigabytes of data of his own motion, just all joint angles of his motion were recorded simultaneously. And we did a dimensionality analysis, a local dimensionality analysis, and figured out that basically most areas just have on the order of 5, 6, 7, 8 local dimensions. And that means if you have these kind of thin distributions, you can actually use learning techniques which basically find these kind of, I think they're called in pancakes at some point, these thin areas and learn in them. And I just sketched that for a moment. You can actually take now these kind of locally weighted learning approaches, make them a little bit Bayesian, and basically this is linear regression, the standard linear regression with parameter beta, inputs, outputs, Gaussian noise assumption. And you can work on this a little bit, can change that in adding some hidden state Z. It's kind of a weird thing. It takes essentially linear regression, makes it a hidden state model where you need an EM algorithm to estimate it, but it takes out the matrix inversion entirely. When you take out the matrix inversion, you get actually the ability to put priors and hyperpriors on your regression parameters and start sparsifying and regularizing very efficiently. So that creates what we called at some point variational Bayesian least squares approach, which is a very robust learning system for high dimensional spaces. And yeah, I'm not going to go into, don't have enough time to all of these things. But in the end, you basically can now take data points, take this function again, create data points, which is 3D, put it into a 20-dimensional space, learn with techniques like this in this high-dimensional space where you know the data is actually locally low-dimensional, and then basically rotate it back into the original space, and you get notice that you get a nice function approximation. Here's another example of a robot learning. So this robot actually uses a similar technique, and it actually just learned how to control its own dynamics and the mapping from external space to internal joint space, what is called inverse kinematics, and to track this ball. The fun thing is, this is all it takes to learn. It learned literally in a fraction of a second. This is, again, these techniques, these learning techniques are meant to be fast. They will not be as accurate and nice as a big Gaussian process, which has a different way of optimizing for accuracy, but they can learn incredibly fast. And another example is a robot, which basically this robot learned how to do this pull balancing task. And one important part was essentially that it had to learn its dynamics model. The dynamics model which we had for this robot from CAD data was just not sufficiently accurate to models. Okay, good. I have one last point. So it was a little bit about model learning. The important message which I really care about is that the way we generate our own data in robotics and the requirements on learning data efficient and fast and in real time create some different constraints on learning algorithms. And there's not so many people who work on techniques like that which we can insert control. And there's going to be much more work. Let me go back for a moment to reinforcement learning one more time and just add a little bit to what Jan Peters was talking about. I'm talking about model-based robot learning. I just want to re-emphasize then to go away from models and you can learn without models. And then at some point you can put this all together in bigger learning systems. So control diagram. So how do we think about a control system? One more time, you've seen this before. Here's your robot, motor system, whatever you want to call it. It has a feedback controller, negative feedback controller, some kind of feed-forward controller, and we assume that there might be a planning system. And we use these kind of differential equations which kind of encode planning policies, but it's not important. There are some task parameters, perceptual parameters which come in there. This is what basically the system needs to spit out desired trajectories which are realized by this controller. And what we are interested in is essentially, for instance, how to use techniques to learn planning systems. That is now a trajectory optimizer or something like that. And as Jan already talked about, well, reinforcement learning is a really nice method to do that. Jan talked about the entire spectrum of reinforcement learning from basically these traditional value function approximation techniques or value function-based methods to a little bit of trajectory-based reinforcement learning. And we are really, over time, and I've worked with Jan for many years, we really came for robotics to the insight that we really want to work with trajectory-based optimization techniques. They are only local optimizers, but hoping that we can represent value functions in a 50 or 100 dimensional state space seems to be daunting in robotics. Don't get the data to constrain that. We cannot do AlphaGo-like things, at least so far. So what we think about then is essentially that we basically get a robot usually going by teaching it somehow an approximate movement to get started. We have something like an objective function, it's an optimization function, and then we do trial and error learning in order to get better. Just to re-emphasize why value function-based approaches are not so attractive. If you try to represent the control policy or the value function for a simple task, and this is a pendulum which is hanging down, people try to swing it up. And it's under-actuated, so you have to swing back and forth before you can swing it up. And it's kind of interesting to just look at the functions which you have to deal with. So this is the policy which tells you at every moment of time which torque to apply at that one joint. This is the value function which tells you how good you're doing at this moment, where you should go next in order to do better. But what is kind of interesting to see is, for the simple example, there's weird ridges, really steep, discontinuous ridges in this landscape, both for the value function, both for the policy, which just tells you if you let a function approximator loose on these things and they smooth over those ridges too much, your control will not work. This is the things you have to kind of worry about. So Trajectory-based methods try to avoid this by never representing these functions. This is why we kind of like it. And Jan talked a little bit about this. I think in reinforcement learning, if you go back in the history, I think from the 1980s to the 2000s, value-based function approaches were really the prime tool that people tried to work with. And then kind of with 2000, people started to work much more with trajectory-based learning for robotics. In other domains, like games or computer science, grid worlds or whatsoever, value function methods are still very prominent. So you can prove things about these things. That is the nice thing. Here, at least, you can prove global optimality and convergence. Trajectory-based methods are not as present. Just coming back to how we formulate problems in there. I just want to show you for a tiny second a fun algorithm which is motivated by kind of robotics control. So trajectory-based reinforcement learning assumes that you have some reward which you try to accumulate over time along a trajectory in expectation, and that's your cost. And you assume you have some of kind of a control system or a policy which has some open parameters which I call B, which you want to adjust. And then you can adjust B, for instance, the gradient descent or whatever you come up. So the gradient in the cost function, try to improve over time. And basically, Jan talked about this. There's many different ways how people have doing this, from gradient descent to natural gradient descent. I think Jan talked about to probabilistic methods, which to, in the end, something which we've worked on in the past, which is path integral methods. I just want to, for 1 second, just mention that, since it has such a nice interpretation how it comes out of control. So the interesting thing about deriving path integral reinforcement learning is it starts actually with my favorite control affine system I like so much. So here's my control system. Okay, x dot equals f of x, g of x times u. And now I'm assuming there's a stochastic component in there, which perturbs my. Okay, that is now a stochastic control setup, which I'm dealing with. Okay, fine. What I want to find, I want to get those u's along a trajectory such that I minimize some cost. So here's my cost function. It can be an arbitrary cost in state. It has to be quadratic in, and you will see in a second why this is necessary. This otherwise you cannot do a maximization operator at some point. And the cost is simply the sum of the integration over all the cost along a trajectory. So this is a very structured setup. This is actually a model-based setup for reinforcement learning, which is actually not necessarily what you want in reinforcement learning. The nice thing is you can show that you can throw away the model at some point. So here's when I do this very fast, this is just, you get the slides. You can read this up if you care about how this works. Path integral reinforcement learning starts with something which is called the Hamilton-Jacobi-Bellman equation. So that's a stochastic version of this is kind of the optimality equation which you have in an optimization problem like that. Looks like that. There's this value function in there. There is my model in there. There's some stochasticity terms in there. And you start manipulating that essentially by inserting our model knowledge in there, solving for some commands u. So that only works if these u's were only quadratic in this cost function. And again, this goes now very fast. Then you basically insert all of this, get a new differential equation, which turns out to be a nonlinear second-order differential equation. You keep on going, you do some tricks to replace some parts, and then it becomes actually a linear second-order differential equation. And it turns out that this differential equation can be solved by sampling. That is essentially what path integral methods are doing. They basically solve an integral through sampling it multiple times, Monte Carlo method, and can thus get the appropriate result. But the nice thing is essentially you get somehow the optimal motor command out of this formalism by simply sampling multiple trajectories and then combining the motor commands which you've been using into an optimal one. So that looks terrible, I know that. But this is just giving you, in case someone wants to look at these equations, a feel for what it looks like. The algorithm which comes out of it is so much more pretty and simple. So that is the entire path integral reinforcement learning algorithm, which says you have some kind of sum of rewards, this you call capital R. You compute the probability of a trajectory, which is the exponentiated reward, negative reward, divided by the sum of all other trajectories which you have been seeing. And then you have a parameter update, which is very easy to compute some very simple algebra. Now, the nice thing is all of this this turns out to come out of this stochastic optimal control approach, and it creates essentially no open tuning parameters except for exploration. Let me make this somehow really digestible. So what this algorithm in the end is doing is actually super easy to understand. So take a bunch of trajectories which you try out. So you want to accomplish a task. You try it out one time, a second time, a third time, and you inject a little bit of exploration noise to make it different every time. Okay, this is shown here. So and this is just a super toy example. This is time. This is position on the vertical axis. There's multiple trajectories which you try to get to this goal. And if you look at the velocity traces over time, you see much more the variation which was injected through noise. Let's assume you want to have some cost function. The cost function is, again, just some terminal cost plus the integration over state and command cost. And so at every moment of time, you can basically compute this capital R, okay, for every trajectory. So if you can do this for every trajectory, then at this moment of time, you can assign a weight to every trajectory, which is this kind of negative exponentiated reward from this time onwards to the end. And the optimal motor command is simply the reward weighted average of all trajectories. That's it. Now that hopefully is much simpler than all the other stuff before. It's kind of cool that such a absolutely simple thing came out of a relatively, at least lengthy derivation from stochastic optimal control. So that turns out to be the optimal solution to a trajectory-based reinforcement learning problem. And last but not least, I'll show you some examples. This will become more plastic. This is all model-based. So how does that make sense? How do I don't want to do everything model-based. I might actually want to get rid of models. So now let's look at a complete control system. So my control system has it's for a robot, has rigid body dynamics. This is this kind of forward model, which I had shown you before. Then it has a control law, which is my feed-forward control law plus negative feedback term. And then it may have a planning system we call the motor primitives, which kind of plan the desired motion. And in this desired motion, there are some open parameters, theta, and those are the thetas which I try to optimize such that my plan kind of minimizes a certain cost. Now, the interesting part of that path integral reinforcement learning is that you can actually prove that the only equations you need to consider in your learning update laws are those which have parameters which you try to optimize, which is just this equation, which is a very simple differential equation. All my rigid body dynamics, even my control law, is not needed at all. So it turns out I can throw away a huge amount of knowledge from models and other things and simply work with a fairly simple equation which has parameters which I can update. And that makes actually this path integral reinforcement learning completely model-free if you want. What is also really nice about this approach, actually, going back to this kind of weighted average of commands, there is no derivative to be taken ever. Why don't I like derivatives? If I touch something, or I should not go there. If I touch something and manipulate something, I get discontinuities in my motion, in all my motor commands and everything else. If I try to take derivatives through a system like that, I get derivatives which I can't control. The derivatives are really annoying in systems which have contact with the world. My phone. So here's a simple example. So here's a little robot. This is a simulated robot dog. Actually, it's the same robot dog which you saw in reality before, but we did this in simulation to not damage the robot too much. This robot basically gets some initial motion how to get across a gap. Let's see whether it works. And this is what a student just programmed in. Basically, it puts some parameterized motion trajectories in there. The parameters is what we try to learn. This was what basically a student could come up with after 2 or 3 hours of parameter twiddling. And then we basically take this as a start and put this into this reinforcement learning approach and see how it improves. And it takes about 10 to 60 iterations, and it gets much better. And it's been learning I think, 600 parameters, I think, in this system, and adjusted them appropriate to get better. And that actually really with very few trials roll out. Another example, this is now actually a robot trying to learn how to open a door. Same idea, the robot was initially given through a demonstration and initial movement how to get to that doorknob. It can also perceive that. And then it basically tries to open it. Initially, what it tries to do, it also tries to minimize interaction forces with the world. So it is super cautious initially, and it learns how to apply more and more force, how to use the right motion trajectory to get better and open the door. The door is instrumented with a little IMU, so the robot actually notices when it gets success. It gets some higher rewards through that. The robot learns this in about 100 to 110 trials, which is quite reasonable from a motor learning perspective. If you put humans into motor learning tasks, they're often a few hundred trials to get them. This is just another example. Robot picking up a pen. And again, initially it tries to not have interaction forces with the world. It's by it's sliding its fingers on the table. And then it learns over time how to grasp the pen better and better, hold on to it, still being very inclined, as you will see in a second. Check that. Just move on. We recently actually, path integral reinforcement learning, because it doesn't use derivatives, is really useful whenever you have contact scenarios like what we just saw. And some of my students work together with people at Google to actually insert this in what is called guided policy search. The idea is you use a local trajectory optimizer to create training data to teach a deep learning neural network. It maps directly from image data to joint tools. And I can't go through the details. In the end, there's lots of little tricks as usually in it to make a complete algorithm work. But the essence is really a pre-trained perceptual network, which then gets added an additional data from a local optimizer, a trajectory optimizer to learn a global policy, how to, for instance, manipulate the story. While this is running, it's completely unclear to me whether you should ever map from image data to torrents. That seems to be a really stupid idea. It is totally cool to try it and see how far you can get with that, but it is not generalizing in any form really robustly. So this is now going into this question which I raised before. How do you want to pre-structure your work? Do you want to learn individual boxes that you have better control over, or you want to learn one big thing? This is here more, it's kind of end-to-end learning. It's more learn the one big thing. Sure, there's a lot of structure in how to do perceptual processing and things like that, and how the last layers are generated. But that is one spooky thing from my point to do this efficiently, and it takes a lot of data and a lot of tweaking to make it. If I made some small point of criticism, this rectified linear unit, this is just a terrible thing. It generalizes into nirvana on one side. That means if I'm going into a piece of territory where I have not been, I have no idea what it's going to do. So there was a reason why we liked little kernels at some points, and at least, okay, if you don't know what you're doing, get 0. 0 is usually good. So lots of questions. People essentially fudge that. They basically make sure that they have all kinds of if-then statements to make sure that at the end, this thing is not spitting out stuff which is completely dangerous. But it's still cool what you can do. that is being a simple message. So this was done in this Google robotic farm, which they have 20 robots and a whole bunch of engineers. Good, all done. So all I wanted to give you is a little bit of a feel for the things people in robotics care about and why people who like robot learning often maybe are more conservative or think differently, or there's different methods how to approach it. And they have different problems to deal with. And they have, yeah, a physical system may just be very disastrous if it does something wrong. We don't have any reasonable learning robots so far. Most really cool things you see with robots are engineered by people. And it took them a very, very long time. Understanding how to use data to bootstrap a robot into performance, exactly as it was mentioned before with a little child, which seemingly does that effortlessly. And taking physics into account somehow, I have no idea exactly how, would be absolutely important to make real progress towards it. So far, people, if they have learning on a robot, they show you something, and then they turn the learning off and never use it again. A continual learning robot is a big. Thank you. Everybody's hungry. Yes.
So you said that just because you have data, you might not be able to learn a model. Is there maybe some heuristics on how to decide if the data set you have is actually learnable?
If you know what you're looking for, you would somehow need to basically create data points and figure out that in response to those input data, what you're getting is noise. So you can look for whether it looks Gaussian or whether it has a huge amount of structure. So you can make some tests for just at least assuming, trying to check whether the structure, whether what you're believing is noise is actually noise, not structure. Otherwise, there's just techniques where you can try to avoid all of this and then go into joint density and things like that, except this is just a very ill-defined problem. I don't know general heuristics. There's tests in the behavioral literature, there's all kinds of tests for Gaussianity and structured things. They're all not so hot. They help you a little bit, however.
Hi. So before you were referring to the data efficiency of learning methods for robotics,
yes,
as well as time constraints.
Yes.
So I was wondering, what is the dimensionality of the problems that are actually solvable with learning control?
It depends. I think I cannot give a general answer to that. Certain problems, as we discovered, are having these kind of low-dimensional properties, so that actually the high dimensionality is not killing you. You just need some kind of local dimensionality reduction techniques which can take care of that. If it were really, really high dimensional, I don't know. Then you're as lost as everybody else in a high dimensional space. I don't know what to put in there. In some sense, the idea of neural networks and kind of sigmoid functions or now rectilinear functions is that these things can generalize very far in high dimensional spaces. There is a role for these things. They are just so hard to understand. But yeah, I don't have a general answer. I think it depends on the problem. People can learn in high dimensional space, but they have to be very.
Hey, I have a question regarding the adaptive control. It has been around for some decades now, and it never really found very widespread applications in any kind of industry setting or even on any kind of real systems. Now, what do you think is the reason for that, and where is this going? And also, do you think this is different for the kind of reinforcement-based approaches that are coming now? And how would they overcome this issue?
So the reinforcement-based approaches are really allowing trial and error in failure. The adaptive controllers, which people developed, or at least the original work on this, you're absolutely right. They were meant to not fail and be really good. And I've been part of actually a project at some point to potentially try to create adaptive controllers with these kind of locally weighted regression techniques for drones, for big drones. And we were told they may have structural failure. That means that don't shoot, okay? Then they have holes at their wings, or something else is missing. The control system should relearn the model of the system to recover. And you can actually do that, and you can show that you recover the 95% what the previous controller could only do 5. Nobody ever flies these things. They're still too scary. The moment it's a nonlinear adaptive controller, you make so many assumptions on the way. What you allow is how big the inputs are, how much the perturbations are. In the Lyapunov functions, in order to make them negative, you have to fudge terms away by overwhelming them with other terms. It's not pretty. It doesn't feel right. So, yeah, people, they don't trust them. As simple as that. There's too big of an error margin still.
But do you think that would be different with the reinforcement learning?
No, the reinforcement learning approaches are worse. So we have no idea about what error margins are. We just put them applications where it hopefully doesn't happen. But flying airplane, again, a flying airplane is one thing. A soccer playing robot which falls over is more tolerable. So it's really the domain in which
So let's thank Stefan once more.
Thank you.